Okay, so let's talk for a minute about the column space of a given matrix A. But before we get there, let's take a look at the matrix U over here, which is an upper triangular matrix resulting from performing row operations on matrix A. The two matrices A and U are certainly not equal. That's why I don't have an equal sign here. But they are said to be row equivalent. Now, when we look at our matrix U, it consists of a row of zeros and two non-zero rows. In other words, row number 1 and row number 2 are the two non-zero rows of matrix U. Now, the first digit in each non-zero row, in other words, the digit 1 here and the digit 7 here, are called leading variables or pivots. So these two numbers, the number 1 here and the number 7 here, are called the pivots of matrix U, or leading variables. So let's just write it down here. So 1 and 7 are the pivots. And of course, following onto that, the columns which contain the pivots, in other words, column number 1 and column number 2, are called pivot columns. Now, the question, of course, is what does matrix U reveal to us about matrix A? Well, first of all, this means that column 1 and column 2 in matrix A are linearly independent. So let's write it down. So column, hey, is that how you spell column? Column 1 and column 2 in matrix A are linearly independent. Now, it also means that these two columns, they form a basis of the column space of A. In other words, any vector in the column space of A can be expressed as a linear combination of these two vectors. So, for example, if we have a vector X in the column space of A, then X can be expressed as